Hello, my driver's ed people, and welcome to today's lesson. We are here on day 2 of our topic, Laws of Nature and Driving. We learned a lot in the first session about things like energy of motion and friction and gravity. And today we're going to dive deeper, cover some new information, go a little deeper in some of the information that we learned yesterday. So without any hesitation, let's jump right in and see what we have in store today. So speed, this is one of the things that we talked about yesterday, but we're going to expand our knowledge of how this applies to the driving task. Specifically, when you're going around a curve, how does speed interact with your driving control? We don't have any control over how sharp the curve is. The curve is going to be however sharp it is, but we do have control over our speed. And so the key idea here is that you need to slow down before you get to a curve. Your energy of motion in a curve will change in proportion to the square of your increase or decrease in speed. The basic idea there is that a small change in speed makes a big change in energy of motion, and that's either way. If you speed up a little bit or you're going a little bit faster, that actually means quite a bit more energy of motion, and that makes it harder for you to maintain control going around a corner. If you slow down a little bit, that helps you a lot. Even that small little bit of slowing down makes a big difference. Cutting your speed in half, which is a pretty big change though in speed, but cutting your speed in half, the force pushing you off the road will be cut 4 times. So that's a squared relationship. Sharpness of a curve, the sharper the curve is, the more traction your car needs to grip the road at any speed. Here we're going to watch a relatively slow speed situation. And specifically, we're watching this little blue car. There's a blue car in the front of the line here, right here, and they're headed into a curve. It's a roundabout, and they're going a little too fast. Now, you notice in this situation, this little blue car actually has a lower center of gravity as this vehicle behind it. This vehicle behind it actually has a higher center of gravity. But if you watch closely, the vehicle in the back slows down. See them hit their brakes and slow down. The blue car doesn't. And consequently, the blue car skids out and this car in the back does not. So the sharper a curve, the more traction your car needs, and the faster you're going, the less likely it is that you'll be able to maintain control. Even slowing down just a little bit makes a difference. Banked curves. Now, banked curves we talked just briefly about yesterday, but it's a really important concept. When you watch a race on television, or if you've ever been to a race, you notice that the corners, the curves on that racetrack, the track is banked, it's slanted. And that's for a reason, because that affects the car's ability to maintain control. It actually increases a car's ability to maintain control. That's right, you can actually go faster around a curve that is banked than you can around a curve that is flat. And if we take a look at a more everyday situation rather than a racetrack, this is the on-ramp at the south exit of 55, just south of Staunton. It's the exit on the south side of Staunton, but this is actually the northbound on-ramp. And you can tell that this is banked just a little bit. It's not a lot like a racetrack, but this right-hand side of the curve is actually lower than the left-hand side. So that allows you to pick up a little more speed safely going around this corner. So we do use banked curves on a regular basis on roadways as well. The load, so that's basically how heavy is your vehicle. What are you carrying in your vehicle? The greater the load, the less control you have. And the reason for that is that you have more energy of motion. So it's going to be harder for you to stop the car, harder for you to make curves without losing control. And so even something as simple as just having passengers in the car. You know, if you add a couple of passengers here, you're probably adding 300 pounds. If you had 4 passengers, you're probably adding 600 or more pounds to the weight of that car. That greatly affects the energy of motion, and that's one of the reasons why we have passenger laws. Vehicle capabilities, these differ greatly from car to car. So here we've got 2 very different vehicles, both of them nice, but this one here on the left, this is a Jeep, and you can tell it's got a high center of gravity. That's going to make it more prone to tipping going around curves. Now, it does have a nice wide wheelbase here, but it's got a higher center of gravity than something like this Camaro that sits low to the ground, is obviously designed to resist that rollover situation. And so this vehicle can handle curves at a sharper speed. Capabilities do differ from vehicle to vehicle. And it's not just turning capabilities that differ, it's also braking capabilities, accelerating. In general, smaller vehicles handle better than larger vehicles. That's a generalization, but in most cases it holds true. Okay, so stopping distance. Stopping distance is actually made up of 3 separate things. Perception time and the distance that you travel during that time, reaction time and the distance that you travel, and braking distance. So let's talk about all 3 of these here. So perception time. Perception time is the amount of time it takes you to work the IPD portions of the IPDE process. Now, we haven't talked about the IPDE process yet. IPDE stands for identify, predict, decide, and execute. We're going to be talking about those things next week. But identifying is simply figuring out what's going on around you. So if we use the common example that we use of a deer walking out into the road, it would be that process of you identifying, hey, there's a deer out there. Predict is you saying, there's a deer there, I might hit that deer, so I'm going to need to do something about it. That's the predict part. The decide is, yeah, all right, I'm going to hit the brakes and try to stop. So that decision-making process. So perception time is all 3 of those things: identifying, predicting, and deciding. Seeing the deer, realizing it could cause you problems, and deciding to hit the brakes. The E, execute, is the actual braking part of it, actually hitting the brakes and bringing the car to a stop. So perception time can be affected by a lot of things like visibility, whether that's a hill in the road or a curve in the road or some other vehicle that's blocking your view because they're in front of you, or weather conditions or trees in the way, whatever it could be, lots of different things like that. Can also be affected by the complexity of the situation. This is one of the reasons that distracted driving is so dangerous, because it complicates the situation. And you see their distractions are listed as well, and they can be part of that complexity. Complexity could also just be heavy traffic, so there's a lot to look at. Distractions include things like cell phones and passengers and loud radios. The average amount of time it takes you to execute your reaction, this is your reaction time, is 3/4 of a second, 0.75 seconds. That's the average time. Doesn't seem like a lot, but if you're traveling 70 miles on an hour on the interstate, you can go a big distance in that amount of time. You're going to go about 100 feet in that amount of time. Braking distance. This is the distance your vehicle travels from the time your foot hits the brake until your vehicle stops. Remember, as your speed doubles, your braking distance quadruples. I want to watch a short video here. I'm going to be quiet and let you watch this.
What you're about to see will change your mind about speeding. 2 identical cars, one travelling at 60, the other at 65. A sudden change in the road ahead. Both drivers first react, and then, a moment later, they brake. And things start to get interesting. Down here, the difference is extraordinary. In the last 5 metres of braking, you wipe off half your speed. So this car is still doing 32 k's when it hits. This one also hits, but only at 5Ks. So no matter how good a driver you are, 5K's difference up there makes 27K's difference down here.
Okay, so I know that those numbers were in metric, and that's not something we're real familiar with, but 5 kilometers of difference, 5 kilometers per hour of difference in speed is the equivalent of about 3 miles per hour of difference in speed. So what they're saying is that if you're traveling even 3 miles an hour above the speed limit, you might not think that's a big deal, but it makes a big deal if you actually hit something, because, if just those 3 miles an hour slower, you're going to be able to take off a lot more speed at the end of your braking. And just like the video showed, it could make a big difference. Okay, force of impact and restraint devices. So we've talked about energy of motion. Energy of motion greatly affects force of impact. So how fast you're traveling and how heavy your vehicle is determines how much force you have when you impact something. And so force of impact, like we said, is closely related to energy of motion. The faster you're going, the more force you have. As speed increases, force of impact increases. As weight increases, the force of impact increases. But here's one of the keys. As the distance between impact and stop increases, the force of impact decreases. And that's really one of the main things that restraint devices are designed to do. They're designed to increase the distance between impact and stop. And so one of the things that your seatbelt does when you've got that seatbelt on, when you hit something, when you get in a crash and your body goes forward, that seatbelt is actually designed to stretch a little bit. And so what that does is that seatbelt is stretching, it's slowing you down, but yet still letting you move forward a little. And that process of slowing you down while you move forward, that greatly reduces the force that's applied to your body. If that seatbelt were super rigid and didn't move at all, then all of that force would be applied to the tissues of your body. So that seatbelt takes some of the force for us so we don't get the full impact of it. And then we also have airbags, and we have crumple zones in the car and all of those kinds of things. And those all added together, a little bit here, a little bit there, all of that added together makes a big difference in whether or not you stay alive in a car crash. I've got another video for you here. This one's a little bit longer, but still not too long. So I'm going to go ahead and play this and let you guys hear it and watch it.
Gasoline has approximately 56 megajoules of chemical energy per liter, which is more energy than you get from exploding the same amount of TNT and is enough to power a toaster for a full day. Cars work by burning gasoline to convert that chemical energy into the kinetic energy of motion of the car, though almost 80% of it is lost as heat in the engine. Still, 20% of 56 million joules is a lot of joules. To give a direct sense of gas-to-car conversion, it takes about 5 teaspoons of gas to accelerate a 2-ton car to 60 kilometers per hour, and about a third of a cup more for every additional minute you want to keep it going at that speed. That might not sound like a lot of fuel, but the energy of a car moving 60 kilometers per hour is equivalent to dropping an elephant, or Stegosaurus, from the top of a 3-story building. And in order for the car to stop, all that energy has to go somewhere. If the brakes do the stopping, they dissipate the energy by heating up. Or in the case of a collision, energy is dissipated by the bending and crumpling of metal in the outer areas of the car. And just like how smooth braking is nicer than a quick, jerky stop, cars are carefully designed to crumple when they crash in a way that lengthens the duration of the impact so that stopping requires less intense acceleration. Lots of acceleration over a very short time is not good for soft human brains and organs. However, people don't like driving cars with Pinocchio-length noses, so most cars only have around 50 centimeters of crushable space in which to dissipate the energy equivalent of our falling stegosaur. That means that while crumpling, they need to maintain a resistive force of about a quarter of the thrust of the Space Shuttle main engine. Over half of the controlled crumpling work is done by a pair of steel rails connecting the front bumper to the body, which bend and deform to absorb energy and slow the car. Most, and in ideal circumstances all, of the rest of the energy is absorbed by the deformation of other pieces of structural metal throughout the front of the car. This meticulously engineered destruction allows a crashing car to decelerate at a high but reasonable and constant rate, just slightly over the acceleration experienced by fighter pilots or astronauts in centrifuge training. As comparison, if cars were super rigid like they were before the 1950s and didn't crumple, they would stop so fast that they would undergo acceleration 15 times what fighter pilots experience in training, which is definitely not good for your internal organs. Thankfully, engineers have learned to make cars with crunchy crumple zones surrounding a rigid safety cell, because fully rigid cars are not good for fighter pilots or anyone else, except maybe robots. This Minute Physics video was made possible by Ford. I was able to talk to an awesome crash test safety engineer there who told me all about the complex physics and engineering that goes into vehicle development and improving how cars perform in a crash. Ford gave me this opportunity because they want you to know how important and carefully designed all the parts involved are, and in particular that the only parts developed and tested to work with their vehicles are original Ford parts. If you want to learn more about why the right parts matter, you can head to takeagoodlook.com. And I personally want to say that making this video has just reinforced to me that regardless of what kind of car you have, big dents and deformations in the body are not just aesthetic problems. They can be safety hazards, too.
All right, so I know there was a lot of sciencey talk in there, but the key concept to take away from that is that the car is designed to increase the distance from impact to when your body actually stops. And so we call these things energy absorbing features. We want the car to absorb the energy, not your body absorb the energy. And so things like crush zones and a padded dash and head restraints that are padded, you're talking about the headrest there, the seat belt, airbags. All of these things are designed to soften the blow. That's another way to think about it, so to absorb energy, so all of that energy doesn't get transferred to you, to your body. Okay, so hey, that takes us to the end of today's lecture. So I hope you understand how important speed specifically is to all of these scenarios. The faster you're going, the more dangerous it is, and that's all there is to it. That's why we have speed limits. That's why the speed limit on regular highways is 55 and not 70. That's why the speed limit on the interstate is 70 and not 80. That's why the speed limit in town is 30 and not 45. I mean, speed limits are set to be as safe as possible while still allowing efficient travel on the roadways. And so what you need to do as a driver is you need to be cautious. You need to follow the speed limits. And when you're headed into a turn or when the weather's bad or any of those kinds of things, make sure that you slow down and stay safe. Hope you learned something today, but even if you didn't, just like my favorite professor, Dr. Phillips, used to say, it's better than a sharp stick in the eye. We'll see you.